In October 1217, as the abbot of Erzberg Abbey, located in what is now southern Germany, gazed at the starry sky, his attention was drawn to a strange phenomenon near the small, arc-shaped constellation known as Corona Borealis. He witnessed a dim star suddenly flare with bright light, then gradually return to its original, barely visible state. This observation was meticulously documented in his manuscript, and may have been the first recorded instance of a recurrent nova. The abbot was likely not the only one to witness this event, but certainly not the last. This cycle of stellar outbursts and fade-outs repeats approximately every 80 years, and notably, the time for its next appearance is approaching. A new bright star, signaling a powerful cosmic explosion about 3,000 light-years away, is expected to appear in the sky as early as September. This is a spectacle not to be missed, as the opportunity to see something similar may only come once in a lifetime. What exactly is a recurrent nova outburst? How and where can it be observed? And what significance does this event hold for modern science? T Coronae Borealis is not a single celestial body, but rather a binary star system, composed of a bright, cool red giant and a compact, hot white dwarf. These two components orbit each other with a period of 228 days. Thanks to high-precision spectroscopy, astronomers possess a fairly complete understanding of this system. Scientists observe the red giant exhibiting changes in brightness, which suggests its slightly elongated shape. It is likely overflowing its Roche lobe, becoming deformed, and losing matter from its upper atmosphere to its compact but massive companion. Studies of this system also reveal a significant hydrogen alpha signal. This signal arises when electrons in a hydrogen atom transition to a lower energy level, emitting a photon with a precisely defined energy. Since this emission appears to change with the star's rotation and does not originate from the red giant, astronomers believe its source is the region around the hot component, the white dwarf. The most probable source is an accretion disk. The relentless gravity of the compact, yet massive, white dwarf draws the outer atmosphere of its large neighbor. Matter that doesn't immediately fall onto the dwarf's surface orbits it in an accretion disk. However, the portion of matter that does reach the surface gradually accumulates there. For T Coronae Borealis, the accumulation process takes about 50 years. During this time, the white dwarf gains an additional mass roughly equivalent to that of Earth. Naturally, as matter accumulates, temperature and pressure increase. Eventually, they reach values at which hydrogen nuclei begin to fuse in the shell. This thermonuclear reaction results in a powerful explosion, a phenomenon astronomers call a nova outburst. It's important not to confuse a nova outburst with a supernova, where the star itself explodes. During a nova outburst, nothing happens to the white dwarf, only its accumulated shell explodes. Thus, it simply sheds excess matter, only to accumulate new material again. Such processes typically repeat, and these repetition cycles can last tens or even hundreds of thousands of years. However, there are a few recurrent novae with very short periods. In this context, T Coronae Borealis is exceptional. It flares up approximately every 80 years, allowing almost every generation to witness this phenomenon. Furthermore, its relative proximity, 3,000 light-years, means it can be seen not only with a telescope. Since 1946, T Coronae Borealis remained largely unnoticed by observers, peacefully maintaining a stellar magnitude of around 10.2. This is too faint to be seen with the naked eye. However, things began to change in 2015. The star slightly increased in brightness to magnitude 10 and stayed there for several months. It then continued to brighten, reaching plus 9.2 over the course of a few more months. Astronomers of the past also recorded similar transformations, specifically in 1938, 80 years before the last outburst. T Coronae Borealis behaved in the same way. Thus, based on the star's light curve and its activity in 2015 to 2016, scientists predicted it should soon dim. This, incidentally, is a peculiarity of this system. After a period of high activity, it first dims before flaring up as a nova. And in March 2023, it indeed began to darken. Therefore, given its current behavior, the nova is expected to erupt sometime between March and September 2024. Don't miss this unique moment. When the star reaches its maximum brightness, its magnitude will be +2. This is comparable to the brightness of Polaris, meaning it will be observable even with the naked eye for approximately a few days, and then for about another week with binoculars. In the quest for this elusive celestial phenomenon, many wonder, where exactly should one look for Corona Borealis, and how can it be recognized in the night sky? The good news for residents of Ukraine is that this constellation is perfectly visible from its territory, and June offers the most favorable conditions for observation. For those with basic knowledge of the night sky and the ability to identify some of its brightest stars, Vega and Arcturus will serve as guides. By drawing an imaginary line between these two celestial beacons, observers will find the desired constellation roughly halfway between them. At the moment of the outburst, the star of interest will rival Alpha Coronae Borealis, also known as Alphecca, in brightness. There's also a simpler way to locate Corona Borealis, using specialized mobile applications that can pinpoint its approximate location. For instance, the free Stellaria map will be a reliable helper. After launching the app and a brief interaction with your smartphone, observers will be able to find Vega and Arcturus, and then the constellation itself between them. Even if you can only distinguish the brightest star in Corona Borealis, it can still be considered a success, as its luminosity during the outburst will be no less intense. A nova outburst is not only a unique spectacle accessible to all who wish to observe it, but also an invaluable opportunity for professional astronomers and astrophysicists to advance their research. This event will shed light on unresolved questions concerning both novae themselves and certain types of supernovae. This is why the most advanced optical telescopes in the world, as well as observatories operating across various electromagnetic spectrum ranges, including radio and X-ray, will be pointed at the outburst. It is known that various phases of energy emission are observed during a nova outburst. The fireball of expanding plasma emits high-energy X-ray radiation. However, as the plasma expands, it cools, and the peak brightness shifts to the optical range. By correlating data obtained from X-ray and optical telescopes, scientists can determine the time interval between these two phases and estimate the speed of the ejected material. Furthermore, a nova outburst presents a unique opportunity for the development of neutrino astronomy. Neutrinos, elementary particles born during such cataclysms, carry information about internal processes hidden from conventional telescopes. Detecting neutrinos from a flaring nova would allow a glimpse into the very heart of this phenomenon. To date, no neutrinos have ever been registered from a nova, which is why precise knowledge of the outburst's coordinates plays a crucial role. The predicted outburst of T Coronae Borealis opens new perspectives for understanding Type Ia supernovae, more powerful cosmic explosions. Similar to novae, these types of supernovae arise from mass exchange between stars, where one of them, a white dwarf, accretes gas. However, to become a supernova, a white dwarf must accumulate mass exceeding the Chandrasekhar limit, which is 1.4 solar masses. Exceeding this threshold leads to an uncontrollable thermonuclear reaction that completely destroys the stellar remnant. Type Ia supernovae exhibit similar light curves, allowing them to be used as standard candles for measuring cosmic distances, including intergalactic ones. It was thanks to these supernovae that the accelerated expansion of the universe was discovered. However, as is well known, astronomers have not yet reached a consensus regarding the rate of this expansion. Various methods, including the use of supernovae, yield slightly different results. Studying T Coronae Borealis will allow for more detailed investigation into the processes occurring in novae, which are smaller in scale but share a common origin with supernovae. If astrophysicists discover any previously unknown features, it could lead to a re-evaluation of cosmic distance measurements and, consequently, the universe's expansion rate, potentially resolving the current crisis in cosmology. No less important is understanding the unique characteristics of T Coronae Borealis, which exhibits behavior distinct from most known recurrent novae. While most novae remain dim and only increase in brightness at the moment of outburst, T Coronae Borealis activates long before this event, approximately 10 years prior, and remains active for a similar duration afterward. This state is accompanied by an increase in its brightness, the reasons for which remain a mystery. Furthermore, immediately before the main outburst, the star inexplicably dims, which also requires explanation. One hypothesis suggests that before the eruption, the white dwarf expels a large amount of gas around itself, forming an envelope that blocks the star's light. Thirdly, historical astronomical observations indicate the presence of a secondary, less intense outburst occurring several months after the primary event. Although its luminosity is significantly lower than the initial one, its occurrence and duration of several weeks naturally spark interest. One hypothesis suggests that this phenomenon may not be a separate outburst but rather an optical illusion generated by complex processes within the binary star system. During the accretion of gas onto the white dwarf, it heats up, which likely affects the companion star's hemisphere facing it. This process was discussed in detail in previous materials dedicated to stellar evolution. After the peak of the outburst, the white dwarf begins to cool, while the red giant's hemisphere remains heated. As the system rotates, the heated side of the star periodically faces Earth, which could be mistakenly interpreted as a new outburst. This effect will be observed until the hemisphere's temperature decreases. In any case, studying this brightest nova outburst will provide answers to many questions currently facing scientists. It remains for us to wish astronomers and astrophysicists to make the most effective use of the opportunities that are opening up. There is a possibility that current forecasts might be a false alarm, and the anticipated event will not occur anytime soon. However, given the star's current state, the probability of an outburst remains very high. As we await this event, we can only hope for favorable weather conditions. Thank you for your attention. Take care of yourselves and support the armed forces of Ukraine. Glory to Ukraine!